Time for another video. This one's comes in kind of two videos really. This is the first video about, well, it's nominally about organic chemistry, but this kind of doesn't have to apply to organic chemistry, because you can have molecular substances that are not based around carbon, and that applies. Not so much that, well, it doesn't apply, but you can do those three with things like germanium chloride or something. So just want to get across the types of formula that you're going to have to get used to doing. Now there is a further one which we'll mention in a moment. These are all for the same substance. This is all butane. So molecular formula, and this is one of those videos where it's worth stopping it and writing down what you need to know. Molecular formula literally just tells you how many of each atom there are. Sometimes molecular formula has a little functional group thing. I'll show you. I'll do some other examples in a moment and you'll see what I mean, but you break up part of a molecule to show you the structure a little. Structural formula tells you, in the case of this is butane, the sequence that the carbon atoms are in, because that doesn't have to look like that. There is an isomer of that methyl propane which doesn't have that structure. So structural gives you some indication of the way the molecule has been put together. Displayed tells you every single bond. Now this is one of the mistakes that people make if they're asked to draw a displayed formula in an exam question, is that they miss out one of the bonds. The classic is an OH, which needs a bond between the oxygen and the hydrogen. People miss it out, lose the mark. Because displayed formula, the definition is every single bond is shown. And then the new, and you will have met those possibly at GCSE, but this is the new thing to A level. This is a skeletal formula. And you see a lot of skeletal formulae as you go through chemistry further and further, because it's really is a shorthand version. It saves time. These things take a nightmare in terms of time to do compared to this, as you might imagine. Looking at it, it's done. What does it mean? It means every line represents a bond between two atoms. Those atoms are unnamed, so therefore those atoms have to be carbon. So that represents CH3, CH2, CH2, CH3. Never ever are these hydrocarbon hydrogens put on. You do put it on when it's not just the alkane type or alkene type hydrogen. But that just represents 4 carbons in a line. It's not 4 in a straight line because you wouldn't see, and secondly, they're not in a straight line, they are in a zigzag when you look at the bond angles. So there you have that. So that would be 1 carbon, 2 carbons, 3 carbons, 4 carbons, 3 lines, 4 carbons, because there's a carbon on either end. I'm going to put a set of different examples on the board, but I obviously need to get the board sorted for that. I'll see you in just a moment. So here's different structure. This is an alcohol. But here you've got the OH identified in the structure. The hydrogen, you could have C3H8O. Oh, I lost count there. C3H8O. But often you still do that to say, oh, it's going to be an alcohol, because there is a way to put that structure together of C3H8O that's not an OH. So it kind of points you in the right direction. It's not necessary. C3H8O would be perfectly acceptable, because it's right. Here's the structural. Now here you've got an introduction of a bracket to say that the OH is a discrete group and it is therefore attached to the second carbon. So the carbon and then what's attached to the carbon. Here's the actual displayed formula. Here's an example of a bond that gets forgotten when people do this, because they're so used to doing OH like it is there, is that you forget to put the bond between the O and the H, mark gone. Displayed formula, every single bond, including this one. And here is the skeletal formula. Now you can see how much quicker that is to draw than any of those other structures. And it tells you everything you need to know about the whole way that the molecule is put together. That's it. I'll just put one more further set of examples on, and then we're done. This is obviously linked onwards into how do you name these structures, which is the video that comes shortly after this one. But I'll see you in a moment with some more molecules. So last example, just to make a couple more points. C3H6Br2. Where are the bromines? Molecular formula doesn't tell you. Structural formula tells you that there's one on the first one, one on the second one. No brackets around the Br because it's a single atom. It's not a group like OH was before. And here is the displayed formula version of that structural formula with the bromines there. Now, some things people say is, does it matter whether I put the bromine there, or there? No, they're identical because that isn't the shape. The shape is three-dimensional. So each one of these hydrogen positions is equivalent and same there. Obviously you don't put the bromine on the middle one because it's on the first one and it's on the third one. And then when you get to the skeletal, it looks a little bit different to last time because because bromine is not hydrogen, you have to have a bond out to the bromine. So the bromine comes up, so there's no carbon at that position, similarly no carbon at that position. That's the bond between carbon and bromine, that's this bond here. So there is one carbon, so there are three carbons. 1, 2, 3. And a bromine, which needs a bond attached on the end. There is one further type of structure that you have to be able to draw in terms of a type of formula, but I'm going to treat that separately. I'm going to do that in just a moment. And then we're done. And we're on to a naming stuff. So I'll just get the board sorted for a three-dimensional and I'll see you in a sec. So three-dimensional drawings, obviously you've only got a sheet of paper and an exam when you're drawing them in your notes and things, look like that. Now they're always based around the fact that you have 4 bonds, and it's done by looking at the surface that you write on, the sheet of paper that you write on. So this here and this here are in the plane of the paper, as it is said, or on the surface of the paper. So you could have here an OH group and you could have here a hydrogen, for instance. And then you have these two. These are the two that make it three-dimensional. This one here is out the front here. The one with the lines disappearing off into the distance is back. I can see it round here because it's behind the board. Can't go behind the board in a classroom, screwed to the wall. But what we're saying is you have one out the front, one behind. This makes this, because of the way it is, a tetrahedral, well, it's tetrahedral carbon in the centre. And so you could have a chlorine on there and you could just have another hydrogen on there. I have a habit of making the one on the one that fades off into the distance, the hydrogen is smaller than the other ones. That's merely me being not particularly artistic. You don't have to do that. You can make them all the same size. Now, getting this to look like that can take a bit of practice, because often when people do them, they go, it looks really awful. And I've taught people over the years who said, I can't do the three-dimensional drawings. But actually, when you look at what they've done, it would still get the mark. They're fairly forgiving. But it does have to have a sort of solid blocked triangle. You don't have to shade it in, although you'll see it shaded in books. And then this single hatched one, as it is often called, over there. Does it have to be on the left? No, you can flip the whole thing round and have the ins and the outs on my side and have the ones in the plane on the other side. It's merely just a rotation of the molecule. This is important when you come to the types of isomers that there are, because this is a way of representing one of the types of stereoisomer that you need to be able to do. It's a year 13 concept for almost all courses. So you need to be ready for being able to draw three-dimensional things in all manner of molecules, not just organic ones, because you have this in and out thing in many other molecules that are not organic. But it also comes into play when you talk about optical isomerism in year 13. And that's it. I'm going to go on straight on to making a video about naming. So I'll be seeing you very shortly, like we should. Thank you very much for watching, and I'll see you soon. Bye bye.